Hi again, dear students. Now I'm going to give you a trick about the chapter 4, section 3, about logarithmic function and the natural logarithmic function. So in the logarithmic function, when you say logarithmic function, you mean log of any function with the base a. In general, the formula is like that. Okay. In general, the formula is like that, and they are the inverse to each other. So you have exponential function, for example, f of x is equal a to power x. So the f of inverse of this function, f inverse of x is equal to logarithmic function with the same. So it means that they are the they are the inverse of each other, and vice versa also true. So for this function, the important things here, as I told you, the graph and properties. So do not forget, also in the 4.3 we are going to we are dealing with the logarithmic function. The important things here is what? Graphs and properties. Okay, dear. So now I'm going to the graph. First things, as usual, this example is try at home. Why? Because we need the example 1, we need more things about the calculation. So we have no calculation, so you can do it easily. Also, the example 2, try at home, there's a little bit things about how to find the relations between logarithmic and exponential function. Our property graph, the graph of the logarithmic, the graph. We have I will leave these properties to later, because I'm directly going to the graph, and then I'm going to join the logarithmic and natural logarithmic together in this session. So the graph of now I'm going after the page. I'll leave the page, half of the page 170. Okay, now I'm going to page 180, and we are going to here I'm talking to I will clarify for you the graph of the logarithm. The logarithmic function look like an exponential function when we sketch the graph. For example, I say f of x is equal to log of 5 to x. The graph is like that. Here's, if I put log of 0, I will get 1. So here's the graph of log of what? Here's the 1 and 0. 1 over x, 0 over y. So here's the function. Okay, so the same thing, the same formula for example, g of x. If I see, let me see the red pen, g of x is equal to log of 2 with the base 2, log of x with the base 2. So in the same manner, in the same way, I have the same sketch like that. Okay, dear. So you can see that they are not different. So if I have another function, I say I have something like that. Okay. So that's why the important things here, the shape will not change, and we are not caring about the exact shape, but we are caring about the intersection point and the shape in general. So f of g of x, y is equal to like that. Okay, dear. In general, we have the graph like that. Okay, and then follow your example 5 and example 6. Which they are very important, and they are those formula that you can, or that I will bring them in the exam or in the quiz. So I'm going to example 5. They are very helpful if you can see, in case I have what for a example 5, page 118 in your lecture note. Part A, if I have g of x is equal to minus log of 2x. So how we deal with this one? First of all, before you are sketching the requirement graph, please sketch the original one that you have 1 and 0, and do not forget this is the outside minus, so you know the outside minus means that reflection, and which the reflection is with what, with which coordinate, with which axis. You know, x-axis will be our mirror, so the reverse of this part is like that, and the reverse of the other part here will be like that. Okay dear, will be like that. So you can see there's the reverse of this function, which is a log of minus log of 2x. Okay dear, so and you can be a curve really, because we have a curve like that to be more real with our question. And part B is what, sketching the graph. Look, really one of the second is also important. Why? Because we have a minus here, and you know the minus inside the graph means that what means that we have if it's my original one, means that y-axis is our mirror because inside. So if y-axis is our mirror, the curve will be reversed to that part, and I will get what, I will get the shape like that. You know, here's this point is 1 and 0. How about here? You should know it's minus 1 and 0. Okay dear, that's all the important things here. And do not forget about that the reversing about inside and outside depends on the x-axis and y-axis. Now I'm going to example 6 in page 119 in your lecture note, and we have, I think, how many examples do we have here? Let me check. Now we have also two more example, part 2 plus log of 5 6. You know, first of all you have what, you have the original one with 1 and 0, and now for adding 5, because the addition is outside the function, means that going to up or down. So we have got a horizontal shift. So I will get what, if I put 0 I get to be 1, I will get 2. So this part will be equal to what, if I put 1 to here I get what, and you know log of 1 is equal to 0, okay, for any base. So if I put 1, I get what, I get 1 2. Why? Because 1, if I put 1 I get 0, so 0 plus 2 2, so it means that 1 and 2. Here's my point, which they are very important, and I will give these properties later. So this point is 1 and 2, so that's why I told you do not forget about 3 fundamental things here. Is the what, first of all shape, it's like that. The second is points, and the third is what, is the intersects. So do not forget about the shape and the reversing and doing graph like that. And part B, if you have part B, say h of x is equal to log of, okay, 10 or anything. So okay, don't different 5 10 2. For me the bases are equal because we don't really mention any things about the base, so the base does not affect our graph so much. So if I have h of x is equal to log of x minus 3 with the base 10, so in that case, careful, the original here, okay, sorry, on 0, and do not forget about they have a, from the beginning till now we have a asymptote here with the y-axis, okay, it was our asymptote. So I have 1 and 0, my function here is between 1 and 0, and the asymptote is 0. So now I have what the given example is, say the given exercise say find this one, and you know inside, if it's outside additional multiplication, means that we have a vertical movement. Now I have a minus and plus inside the function, means that we have a horizontal movement. So maybe we are going to right or left, but we are going to what, we are going to 3 units from here or from here, up to you. So you can say we are going 3 units from here, or you can we are going to the left side to 3 by 3 units. How? So I have a 0. Now I'm counting steps. 1, 2, 3. So means that 3 will be what? Will be our new asymptote. Okay, and so we need number 4 here. Why? Because I have an intersection. After the intersection I have a 0, 1. So I have a 1 unit here. So it means that I have something like that to that. Okay, this is the 4 and 0. So please, this point, they are very important. Be careful. And we have, and you can repeat the video if you didn't understand, because this is my original, and we have x minus 3 means that 3 unit to left. So I'm going to 1, 2, 3. My der kanar, my asymptote, it will be what? It will be 3. How about my intersection? I'm going to the other part by 3, shifting to the left by 3 units. So 1, 2, 3. You can see it. Okay, so that's all that I mentioned in the this part, and I'm going back to page number 170. I'm going to talk about logarithmic. Before I'm going to talking about the properties, I'm going to talk about the natural logarithmic and give you more graph about natural logarithmic function. Okay. Okay, so in case I say what's a natural logarithmic? Natural logarithmic function is just ln. Rename log of x by 2. We have here ln of x. That's all. So what's the relation between log and ln? They are the same. The ln is the special case of the logarithmic function, or log f of x of ax is the general case, and the ln is the special case. So what's the relation between them? In case if your function, we say maybe 2, maybe 3, f of x is equal to 2 of x, we cannot say anything. If my function is with log 10 of x, we can write this one as a log of x without mentioning the base. Why? When we don't mention the base, we don't write anything here, means that our base is what? Is 10. How about if my base is e? You know, e is natural exponential. So we don't want to write these all together, we just write down like that. So we see f of x or y is equal to ln of x. Okay, dear. So means that ln is what? Is the logarithmic function with the base a, e. Okay, dear. So that's all. So here's the relation between log and ln. When e, we have a log in, then I have got what? I can say I have a ln. That's all. And comparing the property of page 117, there you have properties which they are talking about the property of logarithmic function. In the other page, for example, in the page 120, you have another properties about natural logarithmic. So what's here's the relation, the page 120. So what's the difference or similarity between these properties? They are the same, really. In real, you can find them in the 120 and 170. They are the same properties. This one with dealing with the log, and the other part is dealing with what? Is dealing with ln. Okay, dear. So that's why I am going to talking about these properties together. Properties. Okay, when I say properties, I have a log in page 170 and len in page 120. Okay, dear. So the first property we have log of a, what means that any base for 2a, if I have 1 instead of x, I will get 0. So how about here? I say len of 1 is equal to 0. Can you see? There's no difference between them. Now for the second part, if I have log of a, with a means that the base is equal to the variable, so I'll have got 1 means, for example, I'll write the example here, log of 2 1 is equal to 0, len of 1 equal to 0. So about example here, if I say log of, okay, log of 2 for 2 is equal to 1. How about here? Here the same, to len of e, which is equal to log of e, you know, now they are the same, is equal to 1. In general, where's your example? Here's my example. I have no more example. So e. How about the number 3? In case if you have log of a, look, we have what? We have a to power x. And I told you these functions, the log and exponential, they are inverse to each other. And you know when the two functions are inverse to each other, they are eliminating each other. So it remains what? It remains just x. Okay, dear. So how about, for example, I have log of 2 to power x, I can say is equal to x. Okay, dear. So how about the third example here? If I have len of e to power x is equal to x. Give me an example. Example is like the same. I cannot change them. Okay, dear. So here's your example. Now, how about number 4? If I have another example. Now, if I have an exponential function, but the power is log. Okay, the power is what? The power is log of x. So now again I have exponential within logarithmic functions which they are inverse to each other. So finally I will get what? I will get x. So the same thing true for here. If I have what? If I have len of, okay, len of e of len of x, so len is inverse with e, so I will get x. Okay, dear. Any questions? For example 2, an example, log of x or x minus 2, for example, I'll say these are inverse each other, so I will get x minus 2. The same thing is true for here. If I have a log of x to 5x, I say I will get 5x. Okay, so now I finished page 2017 and also the page 120, and here's your examples. In the example 3 we have what? I'm not trying to solve for it because really they are obvious and you can do it. So log of 5, because I have 1, and by the property, first property, I can say is equal to 0. How about this one? I will say is equal to log of, so we do this one. How about this one? Because 5 are the same, so a base and the variable are equal, so I can say a by property. How about this example? By this example we can say, because these they are identical, so I have just 8. How about this example? Property number 3. How about this one? Because exponential and logarithmic, they are eliminating each other, as I did it for you. For example, here you have two log and they cancel each other, so they are eliminating each other, and I will get what? I will get 12. How about the examples on this property of len? You can check page 120, and the example, first example, e and len, they are eliminating each other, just remains 8. How about this one? This one is good, can be changed to here, and you know in the first chapter we deal with these property that the property was what was manipulating with the exponential. So now I have what I have just they are eliminating and remains -2. How about here? Don't care about here, is not include. Okay, cancel. Eliminate this example 9, page 120. Example 3 is not include. How about in example 10 also, because dealing with the domain, please try to cancel this page. Okay, now I'm going to cover your analysis Excel. I'm repeating quickly for you. In the page 160, the definition is important, and then page 117, next page, the important things is what is properties, and example 3. So the page 117, going to 118. In this page 118, the important things there, how to sketch the graph, and how about example 5, AB, they are very important. Now next page 119. So we have an example 6, they are very important. It's A and B, and here's your solution. And I told you if you have a no base here, means that you have A is the base is equal to 10. Okay, that's all. And in the next page 120, the important things is the relation between natural logarithmic and logarithmic in general. As I told you, the base means that is equal to E. That's why we don't mention, and we just write down ln. And the properties, they are important. And example 9, A and B, C is not include. And forget about example C. How about the graph of the ln? I told you, here's the graph of ln, is not difference with log. So if you want to try to sketch ln of x, just do it like that. As we have as a shape, you can see it look like log of x to any base. Okay, dear, that's all about 4.3, and you can find you have a lot of good example. Thank you for watching the video.